Okay, I want to go over the textbook ZIL has, I think, a really good coverage of second order differential equations. It's slightly different. The terminology is slightly different than what we covered in the materials in the previous videos. But I want to go over this because I think it does have some aspects to it that are superior to what was in the other textbook. Also, it gives you a different point of view, and I really like his summary and the way he expresses some of the topics. So, we want to just basically look at the textbook, and I'm going to go through the things in the textbook with you so that we can be sure all of this is covered. The slides from this part of the textbook are not super great, so we'll just use the textbook itself. So the first thing I want to look at is what we're going to focus on here are homogeneous linear equations with constant coefficients, and those are the equations of the form shown here in equation 1. So your A's are your coefficients, and they are, in this case, real constants, and A sub n is not equal to 0. And then we just have derivatives in y in decreasing order, and then that's equal to 0. So the 0 on the right-hand side of the equation says that this is a homogeneous differential equation. The way it's constructed as y and its derivatives says that it's a linear equation because the coefficients are constant. So this is a linear homogeneous differential equation. So if we first look at what's referred to as just a second order equation, so in other words, n is equal to 2, we get an equation that looks very much like equation 2 here, where a, b, and c are just constants that have been substituted in. The slight difference in terminology in this book is we're calling this an auxiliary equation. A lot of people will call this a characteristic equation. A lot of people will use the differential operator d. In this case, we're going to make an assumption, and the assumption is that the solutions to this equation all have the form y is equal to e to the mx, where m is something we will discuss later. Now, the thing about it is there are some theorems that we won't really prove in this class that basically say if you have a higher order differential equation with constant coefficients that is homogeneous, the solutions are all exponential functions or some sort of exponential function combined with polynomials. So because of that, we can make this assumption that we have this solution y is equal to e to the mx, and we'll figure out what m is later. So as we've discussed before, one of the basic fundamentals of approaching solutions for differential equations is you make an educated guess at a solution. Then you take that solution, substitute it back into the differential equation, and you force it to fit or to be true. So we're going to take y is e to the mx, and y prime is me to the mx, and y double prime is m squared e to the mx, which is just our assumption for y and its first and second derivative. And we're going to substitute that into this differential equation, which will have us end up with the equation shown in this line here. So let's highlight that if I can. See if we can. Yeah, so that'll result in this equation here. And notice that this e to the mx is common to everything, so we can factor it out front, and that leaves this expression here. Now, because e to the mx and this expression, this polynomial expression, multiply each other, we can't really, if we want this to be true for all values of x, we can't have e to the mx be equal to 0 because that would only be guaranteed to be true when either m or x is equal to infinity. So that's not really a true solution. So the alternative then is that what multiplies it has to equal 0. So that's what leads us then to equation 3. So equation 3 is known as an auxiliary equation. We refer to this also as a characteristic equation. Mathematicians probably have some hair differences between the two, but in engineering we kind of use them simultaneously. So this is an auxiliary equation, and what we're trying to find out is for what values of m will this expression be true. So basically you solve the quadratic formula for m, and you get two results, m1 and m2. And there are, as we discussed in class last time, three possibilities. First possibility is that M1 and M2 are real and different. The next possibility is that M1 and M2 are real and equal. And the final possibility is that M1 and M2 are complex conjugate pairs. All right, so I just want to say that if you had an even more complicated differential equation, higher order, so third or fourth order, we basically would get the same sets of results. It's just that in a differential equation, you have the number of unique solutions that you generate has to be equal to the order of the equation. So here we have an M1 and an M2. If we had a third order differential equation, we would have to have an M1, an M2, and an M3. And a fourth order equation, we'd have four values of M. So in other words, the number of linear independent solutions that we'll need to add together is equal to the order of the differential equation. And that's true of all differential equations. All right, so if we look at case 1, where we have two unequal roots, m1 and m2, and they're both real, we basically have two solutions. y1 is e to the m1x, and y2 is e to the m2x. And m1 and m2 will actually be numbers based on the values of a, b, and c. These are linearly independent, and so they form what is known in differential equation theory as a fundamental set or a basis set of solutions. So given that, then we can say that the general solution y is c1 e to the m1x plus c2 e to the m2x. So when you have these linearly independent solutions that satisfy the differential equation, the general solution is a weighted sum of the independent solutions. C1 and C2 are constants that can be determined if we have boundary conditions or initial conditions on our differential equation. Okay, the next thing is when M1 is equal to M2, then basically we only generate one solution. Y1 is e to the M1x because M1 and M2 are equal. So there is a theory basically that gives you a second solution of the equation that's discussed in a previous section of the book. This is referred to as a degenerate solution because you have two solutions that are exactly the same. So I'll leave you to read the section about how this equation given is derived, but basically you will get a second solution. So if we look here at equation 6, you have your C1 e to the m1x, and then your second term is C2x e to the m1x. So what's in the exponential is the same. You just have a term that has an x present. And that is common, by the way, independent of the order. So if we had a third order differential equation and the result was one single root. So for example, if you're solving an auxiliary equation that is y cubed minus 1 is equal to 0, then y cubed is equal to 1, and so y would equal to 1 and y would only equal to 1. So in that case, you would have like a third order root. In that case, you would have an e to the mx, x e to the mx, and an x squared e to the mx. So these real repeated roots generate, in addition to the exponential term, they generate that exponential term multiplied by a polynomial in the independent variable. All right, the third case is that we would have a complex conjugate pair. So M1 and M2 would be complex. We'll call M1 alpha plus I or J beta. M2 alpha minus I beta. Alpha and beta are both real and they're both greater than 0, and I squared is equal to -1. It's the imaginary. All right, so basically you just use what we had in case 1 where you have two distinct roots, only they're not real. So instead of substituting M1 and M2, you're making the substitution of alpha and beta. Now, because in engineering we don't like working with complex functions. We prefer to work with real functions because we prefer to work with something that can be measured in the lab. Then basically you use Euler's formula, which says that e to the I theta is cosine theta plus I sine theta, and you do some algebraic manipulation. And after you do enough algebraic manipulation, then what you find is you have the expression given in equation 8, where you have e to the alpha x c1 cosine beta x plus c2 sine beta x. So you have, this is called a damped exponential, or I'm sorry, a damped sinusoid. In real world problems, alpha is almost always a negative number, because we tend to not work in engineering with situations that have exponential growth, because exponential growth, as we've discussed before, typically doesn't last very long before the physical system becomes unstable. So this plot here is an example of what a damped sinusoid looks like. You can see it's oscillating, but then that oscillating is multiplied by exponential decay. So it's oscillating, but it's also, its oscillations are dying away. All right, so here's a couple of examples. The first example gives the following differential equation. Actually gives 3 of them, and you don't have any initial conditions. So the goal here is just to solve for the general form. So if you look at this first equation, substituting m squared for y double prime, m for y prime, and 1 for y, we get the following expression. If you factor that expression, which it's easy to factor in this case, you find that you get 2 roots. You could also, at this point, use the quadratic equation to get these 2 roots. So you get 2 roots, m1 and m2, and then from the previous expression, we just write the total solution as c1 times e to the m1 x and c2 times e to the m2x. So that's that example. Then another example, m squared minus 10m plus 25. Basically that factors into m minus 5 squared. It's a perfect square. So you have a double root here, a double root of 5. Once again, if you don't want to do this, you can use the quadratic formula. You'll get 5. So substituting, this is of the second type where we have a double root, excuse me, that is real. So here we just have c1 e to the 5x plus c2x e to the 5x. And then finally, if we have example C, if you use the quadratic formula, you find that this is a complex conjugate pair where alpha is minus 2 and beta is the square root of 3. So substituting in for alpha and beta in equation 8, we get this expression for y, which is your damped sinusoid. Example 2 is just an example of a similar problem where we have a similar expression, but we have y at 0 is equal to minus 1 and y prime at 0 is equal to 2. So we actually have some initial conditions given. So the first thing that you need to do is find the expression for the general form, which means you have to solve for m1 and m2. They are a complex conjugate pair as given right here. And so our alpha is minus 1/2, our beta is 2. So once again, we're going to substitute into this equation, which is the general solution. And we get something that looks like this, where y is e to the minus x over 2. And then we have our sinusoidal part. Now we want to apply our boundary conditions. So the first thing we know is that y of 0 is equal to negative 1. So you want to substitute 0 in for x. And when you do that, you get e to the 0. c1 cosine theta plus c2 sine theta is minus 1. This second term is equal to 0 because the sine of 0 is 0. This entire first term is equal to c1 because cosine of 0 is 1 and e to the 0 is 1. So that gives us c1 is minus 1. If we now take the derivative of y, we get the following expression for its derivative, and this should be a y prime right here, this term, not y, because they have already taken the derivative. Actually, Is that the case? I guess not. I guess this is before the derivative is taken. So if you now take this expression and take its derivative, and then you use the fact that we know that y prime of 0 is equal to 2, you get an equation for C2, and you can determine that C2 is equal to 3/4. So substituting in the -1 for C1 and the 3/4 for C2, we get this expression. And so here's a plot of what that function looks like. This is a damped oscillator. And one last thing to look at is that there are a couple of differential equations that are a little unique. Um, the one that I want to focus mostly on is this first one, where we have y double prime plus k squared y is equal to 0. The second one, we just have a minus sign. It turns out that if you look at this, if you move the k squared y over to the right side, then what you can deduce is that this is a problem whose second derivative is equal to negative of the original function. And so that would be from the sine and cosine. The other option is to solve the auxiliary equations, finding that you get imaginary roots only. So this would mean that your alpha is 0 and your beta is k, or some constant, which means that when you substitute into that equation 8, you have an e to the 0x, which is just going to go to 1. So y is purely sinusoidal. So this is a pure oscillator. It doesn't have anything that is going to damp it. It's just going to oscillate like a sinusoidal function. If you have a negative sign here with for this expression, then it turns out that the solution is two distinct real roots, one positive and one negative. So you would have C1 e to the kx and C2 e to the minus kx. You could do some hyperbolic sine and cosine substitutions to get expression given in equation 11. It's just an alternate form based on a variation of Euler's equation. So, on the hyperbolic sine and cosine. So anyway, that's just an overview of the materials in this section. I think let's talk really briefly about higher order differential equations, and then we'll call it done for this video. If you have a higher order differential equations, basically, first of all, let's say you have the general solution is going to look like this. So the general solution will be a sum of exponentials. So what you have to determine is, what are your m's? Are they real? Are they complex? Are they repeated roots? If they're repeated roots, then basically you're going to get terms that look like e to the m1x, x e to the m1x, x squared e to the m1x, depending on the order. So if you get a third order root, you'll generate 3 terms. If you get a 10th order root and the roots are all equal, you'll generate 10 terms. So you could conceivably have this kind of solution for part of the roots and complex conjugate pair. Or you could have repeated roots and distinct roots. So it's basically going to all be a sum of whatever you solve for. So here's an example of that. Not going to belabor the third order differential equation too much, but here's an example of that. If we substitute m to the n for the order derivative, we get an auxiliary equation that looks like m cubed plus 3m squared minus 4. And I love the way the books always say this should be apparent by inspection. To most of us, it's actually not apparent by inspection. MATLAB has a command called roots, where you can enter a polynomial and it'll find the roots for you. But let's just say that one root is m equals 1, and the other root is a double root at minus 2. So because we have, so what we have is we have one term that is a distinct real root, and then we have 2 terms that will be this double root of minus 2. So that means your first term, incorporating this root of m at 1, is going to look like c1 e to the x. And then your next two terms are going to be this repeated root. So we'll have a c2 e to the minus 2x, and then we'll have a c3x e to the minus 2x. So that's the way that works. And the thing to remember is if you have an odd numbered polynomial, an odd ordered differential equation, you'll always generate at least one real root. If you have an even numbered differential equation, there's no such rule. So that is that. And I'm going to pick out some practice homework problems for you to look at and highly recommend utilizing this particular method.